ionic, covalent and hydrogen bonds. Ionic bonds, there are electrons gained or lost. An atom gives off an electron or gets one. If the electron gets an electron, if an atom gets an electron, it has too many electrons, and therefore it is negatively, and it is an anion. If the atom loses an electron, it has more protons in the center than electrons, therefore it is positive, more positive protons than negative electrons on the shells, and therefore because it is positive, it is a cation. Covalent bonds are similar, but where the electron is shared. It's not given away like ionic bonds which form ions, but it is shared, and they form molecules. So the shared is basically the electron is basically the whole time in the middle of these two atoms which are sharing it. If it is shared between two atoms who have not the same, an unsimilar force of pulling at the electron, then it can be that one, like in oxygen and water, the oxygen is pulling stronger at the shared electron as the hydrogen is pulling at the electron. And that would be now a polar covalent bond, because they are polar. The hydrogen has its electron a little bit pulled more away from it as it has technically less electron, so it is more positive. It has positivity. The oxygen has pulled it towards it. It had become a little bit more negative. It has no negativity, so that is a polar covalent bond. They are polar. Non-polar is if it's between, for example, two atoms which have the same pulling force, and it's just in the middle, non-polar. And the hydrogen bonds. Now, in that example with water, the H2O with the two hydrogen and the oxygen, where the oxygen is pulling stronger at the shared electron in the middle, there the hydrogen has become a little bit positive because the electron was a little bit far away from it. And now that negativity gives it a little attraction force to other, a little positivity of hydrogen gives it a little bit attraction to negative things, for example, oxygen or nitrogen. And that is not strong enough with force in hydrogen bonds to form new molecules, like covalent bonds, where it is shared. But it is enough by large molecules, where there are hundreds of them, to make a link between molecules, for example, or also to give that whole thing, that whole molecule structure and stability, and the whole shape of it. When there are hundreds of them in a large molecule, that is also important in the human body. So ionic bonds, they are gaining and losing electrons, and positive ones are cation. Positive ones, they have too many protons, and negative ones, anion, they have too much electrons. And the covalent bonds, they are sharing. They can be polar. When one is pulling stronger, they are polar. One has positive, one negative. And non-polar, they have equally sharing between those two same atoms. And hydrogen, that is just if it was pulled away in such a polar covalent bond, hydrogen is negative, is positive, and it pulls to another negative thing. That is according to Gerard and Sandra Gabrowski's Principles of Anatomy and Physiology book, on several pages starting on page 30. But this is no medical advice.
If you click this video away, then please tell me what the reason for it was so that I can improve. Otherwise, hi and welcome. I am trying to learn biochemistry, today chemical bonds, and after we've done that, we're going to do stretching. And if you participate in the stretching, then it's already on this. Chemical bonds. Molecules and compounds are the products of chemical bonds, which act like powerful glue that holds atoms close together. We are saying here there can be two atoms and they can stick together, like glued together, and they are then a molecule or compound through such a bond. The likelihood that an atom will form a chemical bond with another atom depends on the number of electrons in its outermost shell, also called the valence shell. Maybe we're going to explain it. An atom with a valence shell holding 8 electrons is chemically stable, which means it is unlikely to form chemical bonds with other atoms. Neon, for example, has 8 electrons in its valence shell, and for this reason it does not easily bond with other atoms. We already did the ionic bonds, the covalent bonds, and the hydrogen bonds in the previous part, so there's nothing really to explain. It's pretty obvious. And they're kind of explaining what I want to explain, I'm going to do it in a moment, nevertheless. Hydrogen and helium are neon, for example, has 8 electrons in its valence shell, and for this reason it does not easily bond with other atoms. Hydrogen and helium are exceptions. their valence shells only hold 2 electrons. Because helium has 2 valence electrons, there it is, figure 2.2, it too is stable and seldom bonds with other atoms. Helium has also 2 valence electrons. 2. Helium has just 2 electrons and they are both on the only shell, so it's the valence shell. There's figure 2.2. Hydrogen, helium. That's not really an explanation. Why are this? So all electrons are then called valence electrons. All electrons on the outermost shell are called valence electrons. But this is interesting. Even if it is full with helium, or is it a special case with 2, because it has just 1 shell, and the other shells seem to be able to hold all 8. Where the second, third, we had only second and third as an example here. So it seems to be that the first shell can hold 2 electrons, and all the other further one 8. But why does it not get more? I think that's strange. Maybe it gets more. It wasn't used here so far. And it's a bit unlikely. The elements which would have 4 shells, that would be once or 30 or 40 electrons, they're getting very unlikely that these elements exist. They are very unlikely elements with this amount of this amount of electron number. The atoms of most biologically important elements do not have 8 electrons in their valence shells. Under the right conditions, 2 or more atoms can interact in ways that produce a chemically stable arrangement of 8 valence electrons for each atom. The most electrons used in the human body don't have a full shell with its 8 electrons in it. Most of them have 7 or 1 or whatever. And so they are not unlikely to form a bond because they do not have 8, they don't have 8, so they are likely or more likely to form bonds with other atoms. This chemical principle, called the octet rule, helps explain why atoms interact in preferential ways. That is to say, one atom is more likely to interact with another atom if doing so they leave both with 8 valence electrons. So someone who has 3 electrons on the outermost shell doesn't want to come up with another element which has also 3. If they would share them, they both have 6, not 8. Why should they go into this arrangement? It doesn't fit. They rather want to go with someone else who has then 5, 3 and 5, or 1 and 7, something like that. For this to happen, an atom either empties its partially filled valence shell, fills it with donated electrons, or shares electrons with other atoms. The way that valence electrons are distributed determines what kind of chemical bond results. We will consider 3 kinds of chemical bonds: ionic bonds, covalent bonds, and hydrogen bond. We already did them in the previous part of biochemistry, so I just wanted to read it. No, we wanted to read it. Okay, it's just the atom and they all have their numbers, and they're on the periodic table of chemistry, and there's hydrogen the first one and then helium the other one. And then we all the other one down, and the number which we have. For example, we have here as an example, sodium has the number then 11. So sodium is somewhere, I don't know, let's see, somewhere there with 11. The atomic number is 11. The 11 means it has 11 protons in the center in the atomic nuclei and 11 electrons. So the same number of protons and electrons. And the atomic number by sodium 11 means there are 11 protons and 11 electrons on the shells. So all around. The first shell can hold 2 electrons and the other one always 8. I don't know if it gets then more, as I said in the beginning, if it's from 12 or 16, but the second and third 8, probably the fourth and fifth also 8. So sodium has now 11 electrons, 11 protons in the center and 11 electrons. The first 2 on the first shell, and then on the next shell there are 8. Now we have 9 away, and now 2 are missing. Sodium has been 2, so I miscalculated. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 2 plus 8 are 10. 10. So 2 on the first shell, 8 on the second shell, the second shell can hold 8, where 8 one, so we're having 2 plus 8, 10 are gone, sodium has 11, and there's now the 11th one single there on the shell completely alone. And that one can be given off to another electron, for example chloride. Chloride happens to have 17. Chloride has the atomic number 17. That means chloride has 17 protons in its center and also 17 neutrons, and it has now 17 electrons. 2 on the first shell, 8 on the second shell, and 7 on the third shell. These are together then 17 electrons. 2, 8, 7. And this 7 want to become 8. With 8 they are full. They fit then on the outermost valence shell, and the sodium happens to have 1, and it does want to give it away. Then it has again on its last shell the second one 8. So it has 2, then 8, and then 1. If it gives off that 1 on the third shell, it has on the second shell these 8, and it's perfectly happy. So that one gives an electron away, the sodium, and the chloride gets this electron, and they couple up together, and it's now sodium chloride. And a new thing has happened. That's basically what we did. We did it all already in the previous part. So that was the chemical bond part. That means if you were here for biochemistry, you can go directly to the next part of biochemistry. We will continue with something like that. If you stay here and participate in the stretching, then it's very our task. And we're having the feet sitting together, and the toes are going to the outside, the other toes, the heels and the heels. Toes, toes, heels, heels. As far as you can. And then again in. This time stay down, so go into the knees. And up. Legs shoulder wide apart. Breathe in and lift the arms up. And breathe out and go to the side. In into the middle. Out to the other side. In into the middle. Out the hands down and slide with one hand down the leg. And the other shoulder stays down. Breathe in. Out one arm over. Breathe in and out the rib cage. Out into the middle. Breathe in. Out one hand slides down the leg, the other shoulder stays down. Breathe in. And out one hand over. Breathe in and down the rib cage. Out back into the middle. Breathe in the arms up. And out. And now breathe in and reach down with one hand. Have your feet sitting together. And out and up. In on the other side. And out. Again. In. And out. Again in. And out. Hands down. Feet shoulder wide apart and shoulder circles. Back, up, and front, and down. And backwards. And breathe in and lift the shoulders up. And out and down. In and up. Out and down. And the apple plucker exercise. Breathe in the arms up. And reach always with one hand high up. Pretend to take an apple hanging high on an apple branch, to turn it a bit around and then to dip it down. Last two. And the legs wide apart. Arms up to a T. Breathe in. And out, shift over to the side. Again in. And out. Again in. And out and lean onto the knees. Breathe again in. And out one shoulder in front. In and back. Out the other one. In and back. Out one in front. In and back. Out in front. In and back. And out and we're hanging down. Breathe in. And out, go over to one leg. Breathe again in. Then out over to the other leg. Breathe again in. Out back into the middle. Close the feet, but keep on hanging down. Breathe again in. Then out. Again in. And out, come slowly with a round back up and make at the top a backwards shoulder round. also pointing to the outside. We're having an ulnar space between the heels. Breathe in and lift the arms up. And breathe out and sink down. The elbows against the inside of the knees. Breathe in and straighten up. And breathe out and come back up. Breathe again in. Out again back into the garland pose. Breathe in and straighten up. And out again up. Breathe again in. Out and down. Breathe and straighten up. And out come slowly in one straight line upwards. And the hands again. Have a good standing leg. And bring the heel of the upper leg on top of the knee of the standing leg. Don't do this if you could injure yourself. So do it only if you can do it without injuring yourself. Breathe in. And out and down. And again up. The other leg. Breathe in. And out and down. Up. Legs to the side and breathe in and come down. And breathe again out. Again. And out. Now around, breathe in. And out. Again in. Out. Breathe in and close the legs. And breathe again out. That was the stitching. Thank you very much and until next time.